Okay. All right, last time we left off looking at Lab 3, and we did 2 exercises from Lab 3. There's one more exercise that we need to do, and there is, in fact, looping in Lab 3. It appears in Exercise 3. But we added some example of looping in our solution to Exercise 1 in the last lecture that we met in. But in fact, that is a topic that I wanted to cover at this point in the class. So looping is in here. We'll look at that now. And I want to bring your attention to this assignment 1, and I recommend that you pay particular attention to this assignment because it's basically practice for the quiz. So these are the kind of questions that I will ask in the quiz. In fact, probably many or all of these questions came from previous quizzes that I gave when teaching this class. And these are exercises that you do just with the pen and paper, or a word processor. These are not meant to be compiled and run as programs. These are shorter problems that involve reading a small number of lines of code and understanding what the code does. And it also involves writing a few lines of code to solve a problem. And we'll look at this next time. But if you want to get an early start on assignment 1, that would be great. And quiz 1 is coming up. Quiz 1 is going to look a lot like assignment 1. Of course, assignment 1 has material that you're preparing for by doing these labs. And then there is lab 4 as well. All right. Let's go back and look at lab 3 here and solve exercise 3, which is to generate a web page using a program. So before I even get started reading about that, let's just do what we know we need to do. I need to go into the folder, and we need to create a folder, a subfolder for the solution to this lab. And I'm going to add that folder to subversion. Whoops, I forgot the add. So I made the folder. When you create something new, if you want it in the repository, it's a good time to add it right there. Now, it didn't actually get transmitted to the repository. It's just scheduled to be transmitted. The information that what I did was I added the new folder to the working copy. That means I modified that .svn hidden folder that's in the current directory. I do ls-a to list all contents of the current directory. You'll see there's a folder called .svn. Folders that start with a dot are not by default displayed when you view them in a tool like ls. And the information that I want this in the working copy, that information is stored in there. So when I executed that svn add lab033, that modified the contents of this .svn folder. And that is, by the way, a folder. And I'll prove that to you. That's the contents of that folder. And there's just lots of information in there that the system is storing. All right. I'm going to copy. It's easy to work. It's easier, rather than just writing something from scratch, it's easier to make a copy of an existing program. And that's what I'm going to do now. So I'm copying. This is the copy command. This is the source. That's the path name to the to the file that will be the source of the copy, the object that I want to make a copy of. And then the second argument is the destination. That's a folder. I put a slash at the end of it just to show that it's a folder. But I don't actually need the slash. It's just that if this didn't happen to be a folder, if that was a file, I would overwrite the file. But if I had a slash, I'm telling the command that I expect it to be a folder, and I want the copy to be placed inside the contents of the folder.
So what if you put the slash, but the file, it's a file? Like, you want to copy it into a folder, but there's no folder. Will it make it, or will it?
Let's try it. Let's test that. So I'm going to create a file called temp.
Okay.
And it says hi. Okay. Oh, there it is.
Okay.
There's a file called temp. And it says hi. Let's copy, what was it, lab 032?
Yeah.
Let's copy that into temp.
Make it a folder. Yeah. Okay. Okay, cool. Bye.
So no, it's not a directory. All right, let's try it this way. It killed my work. All right, so so just adding that slash, just a little extra insurance that you don't do something dumb. Okay. I created the file. I know the file. It's not in the state that I want it to be in, but let's schedule it to. Let's put it in the working copy of the repository. There we go. I just scheduled it there. But we're not going to write it into the repository yet. And there it is. We have our main.cpp. I do want to remind people that there is the .svn hidden subfolder in there. And I'm going to start up the screen. So we have this business. Yeah, question?
Well, if we're using Visual Studio, what kind of application are we opening to write the web page? Is it just like a normal Windows 32 console?
Yeah.
Okay.
So you will, in Visual Studio, in this class, for all the problems we do in this class, you will use a Win32 console application. That's correct. And if you're in Macintosh and you're using Xcode, if you're running at the command line, you can do it exactly the way I'm illustrating now with, with command line based text editor and C++ to compile the program. But if you're inside of Xcode, if you want to run it graphically, then you need to also create a console application. There's a way to do that in Xcode. All right, let's put that, yeah, we're just going to say okay. Let's just test our environment, make sure that we're all set up, ready to do the development. There it is. Should say okay. Good. All right. Write a program that generates a web page that contains a list of 100 random integers. The program should write something like the following into cout. So we just basically want to print something like that, but we want 100 of these list items. And this business here, we're going to come back and do this. Oh, but I want to add this down here. Okay. We'll come back and look at the other instructions in a moment. You can test your web page generation program by redirecting standard out to a file. To do this, run the program as follows. So we'll try that. And open, yeah, the problem with this example is we can't actually view the web page. And because it's on the remote host, right? But we'll figure out how to do it. Watch. See, when I taught this class before, I was a lot of the students were using Visual Studio and Xcode, the GUI interface, and we're just building things and running the program locally on our machine so we could open the file to view it locally. But now we're working on a remote server, so it's a different environment. But there will be a way that we can figure out how to run this locally.
There is a way. I learned in my last computer class. I just forgot how to do it. No, it's like you write it in Notepad, and then you save it as like a certain extension, and then you use a browser to open it.
There we go. There's the solution right there. That's one way to do it. I was going to commit it into the repository and then copy and paste it, but I think your way is better actually. All right, so let's go ahead and let's copy this here. This is going to have to be outputted, and let's test the process. And I'm just going to start by pasting it in there as a comment. And one by one, we'll take stuff out. Well, let me leave it out here. Yeah, question?
What key you need to press to pass the content?
I used a right mouse button, and it just pasted it in there. But that'll depend on your system, how your system runs. In VI, you need to be in insert mode. See down the lower left corner? I'm in insert mode. And then you have to be in insert mode. Then you just paste out of the clipboard. Now I'm in Windows, right? Pasting into a terminal window that's getting sent to Linux. So it's like right mouse button.
Use your right mouse button, and then it'll bring up a little list, and you just select paste.
But actually, it's different. You know, it depends a lot on what you're working on. The safest way to paste is Control V. Control C to copy, Control V. That works practically everywhere.
Except on the terminal. It doesn't work on terminal.
The Control V doesn't work? Yeah, maybe. All right, so I'm just going to, put the Couts in here. And I'm going to copy. See, I don't want to do this over and over again, so I'm just going to copy that part, okay?
Yeah, your arrows are backwards on the Cout.
Oh, I don't want to copy that. Thank you. And let me go ahead and. It's funny. All I need to do is highlight it. I don't need to. I don't need to copy it into the clipboard. Usually in a terminal window, you just highlight, and at this point, I just right-click, and I paste it in there. Oh, but I didn't get the quote, and I wanted a quote. We'll try that again. Just highlight it, and then I have to use the arrow keys to position the cursor inside the console window, the text editor running in the console window. And when I'm where I want to be, this doesn't matter. I just right-click. What matters is where the text editor cursor is at, not the mouse. And let me go ahead and keep doing this. Right-click. Right-click. Yeah, I'm just going to leave that out. I need to go into insert mode, right-click, right-click. All right, that's to have the job. We get the left part, the left side. I mean, well, it's working now. I mean, in Windows and PuTTY, I'm just right-clicking. Now, and I'm in insert mode. I'm right-clicking. Whatever I highlight, and I'm not copying. I'm not issuing a copy command. Whatever I highlight is going to get pasted in to wherever I right-click. And that. Oh, the insert mode. You just I press Escape to leave insert mode, And I press I to enter into insert mode. I and escape. Only VI. This is only VI. You know, VI is everywhere though. If you know VI, you can do it. You know, Macintosh has got VI, Linux has got VI, BSD has VI. Windows does not have VI. It's not a VI. They're a holdout. Okay. And I just want to add this to everything. Oops. Let's see if that works. Okay. Oh, something's wrong. I think it was just a network delay. Try it again. Yeah. So let's check our web page. Here's one way to do it. This is your suggestion. And we go to, say, the desktop and temp. Temp means I don't have to think about it. If I can't remember it, then I know it should be deleted. All right, so let's create a new file called, it should be a text document. So we all want only character data in it. And let's overwrite that txt argument right there, or extension rather. And I'm going to call it sam.html. That's for sample. It's warning me. Now, the reason I could do that in Windows is because I have done the following setting in Windows Explorer. In Windows Explorer, that's the name of this program that you use to view the file system. And I set this setting here. Hide extensions for known file types. See, if I had that on, the process would be more difficult. Here, now see the .html is now missing. I don't see that. So let's do that whole process again. Let's create a new text document, and we're going to call it. There's no extension. See, we'll call it sam2.html. I want it to be an HTML file. Well, look at the difference.
Still a text file.
It's still a text file. Watch. Let's not hide extensions for known file types. You see, there's a .txt that was appended to it when I created the file, and you don't see it as a regular user. So programmers tend to, they need to see the extensions. Okay, when you're programming, you need to see file extensions. You need to be able to modify them. For a regular user, it's usually a mistake if you change the file extension because you've broken something. So it's good to know about this. Okay, so this will just delete that one. And I'm going to open this not with the browser. I'm going to open it with Notepad. And I will copy this. I think that puts it in the clipboard just by highlighting it. Let me try it and then paste. It did. I didn't do Control-C. I didn't do copy-paste. I just highlighted it inside PuTTY. That is a Unix convention, by the way. So there we have the web page. Let's save that. And now I'll just open this with the default application, which is Chrome browser. We could open it with something else. We could open it with Internet Explorer or whatever. That's another browser. There it is. So we have a list, a web page. It has a list of 2 items, but we want 100 items. So we're going to use a loop to create a list of 100 random numbers. Okay. We'll just leave that there. So this is the point where we need the 100 random numbers right in here. Output 100 list items with random numbers. That's not a perfect expression, but I guess that's good enough. So actually this instruction here we don't need because we're not running locally. If we were running locally, we would use this. So in the lab, you could in fact use this form. But if you're working remotely the way we are now, then the way we just did it is fine. But I want to show you what this does here, okay? Actually, we don't have to build it again. If you look in here, the a.out, that's the executable. When we run a.out, it writes its output into this thing called a standard output stream. The standard output stream can be assigned to different output devices. And by default, it's assigned to the console window. So it's just written to the console window. But we can reassign the standard output to a file. And it's this greater than symbol that you use to accomplish that. So this is called a redirection operator. We're redirecting standard output to a file. So now it didn't display on the console. But what it did was it created a file called sam.html. And that's where it wrote the output. Actually, we need to get rid of this OK. We don't need that. We don't want that in the HTML file. All right, so let's do this. So we need to do 100 of these. We have to list 100 of these list items. Well, you need to read the book to read about looping. So the loop that we're going to look at right now is called the for loop. And the for loop is used in situations where you know exactly how many times you need to repeat an operation. We want to repeat this operation 100 times. So the for loop has three three sections to it in this part of the for loop. This is initialization. The second section is that this is the loop condition, and this is the operation that's done at the end of the loop. So this is initialization. This is the loop condition. So in initialization, what we're going to do is define an integer I and initialize it to 0. So int I, that declares I. It says int I is an integer, equals 0. Let its initial state be 0. This is the loop condition. This is the condition that's checked each time the system is ready to pass through the body of the loop. The body of the loop are all of the statements that are enclosed in these braces. You have an opening brace, 0 or more statements, and a closing brace. These statements are executed as long as the loop condition is true. So the loop condition is going to be I is less than 99. Now, this loop, the first time when the execution reaches this point, we create an I, we set it to 0, and then we say, OK, loop take over. And then it's going to check the loop condition. Is I less than 99? Well, I is 0, so 0 is less than 99. True. OK, so it's going to do the body of the loop. It does this. And then it's going to execute this end of loop operation, and that's going to be to increment I. So now I goes from 0 to 1. And then it's going to reapply the loop condition to check to see that it's still true. And it is in fact still true. It'll do the body of the loop again. When it finishes the body of the loop, it'll execute the end of loop operation. Now I goes from 1 to 2. 2 is still less than 99. We do the body of the loop. So we repeat that over and over again. Eventually, we're going to get to I equal 98. All right? When I is 98, 98 is less than 99. We print this. We increment I becomes 99. And then it shouldn't be 99. It should be 100. Huh? So when we get to 99, 99 is less than 100. So then we do the body of the loop. Then we do the end of loop operation. Now we hit 100. Now when I is 100, 100 is not less than 100. The loop condition now fails. So we continue execution to the next line, next statement, which is down here. So that's a loop. So a loop has, very important, a loop has a loop condition. That's the most important thing you have to think about. A loop. A loop is a group of instructions that you're going to repeatedly execute as long as the loop condition is true. And as soon as the loop condition becomes false, you will stop executing that group of instructions. The main thing to think about is the loop condition. In the while loop, I'll show you what this looks like as a while loop as well. Okay? And the while loop, you don't have the in I, you don't have the plus plus I. That's taken out. The while loop just has the loop condition by itself.
Do we need the command CSUSB up in the top include CSUSB? Or is that from the old?
Yeah, probably don't need that. Thank you. That's very good. That's excellent to take that out. That's unnecessary. Should always remove unnecessary code. In fact, you have, in this class, you're required to remove unnecessary code. And that's stated in the syllabus. That's one of the requirements. So when you submit your work, you shouldn't be submitting code that has unnecessary lines in there or that do unnecessary operations. All right. So this should repeat this one line over and over again. So we should get 100 of them. Now look, the counting is a little funny here. This is the classic for loop right here. It starts at 0. And we want to do something 100 times. We start counting at 0. And the loop condition is that the counter is strictly less than the number of times we want the loop to run, which is 100. The other way that we could do this is the way the computer counts. When the computer counts, it starts at 0. It says, I'm going to count the number of chairs here. Ready? I'm a computer. Okay. 0, 1, 2. There are 3 chairs there. That's how the computer counts. Obviously, a human goes 1, 2, 3. The last number I counted, that's my number. The computer doesn't do that. They start at 0. They go 0, 1, 2. The count is 3.
So in that case, shouldn't that should be 99 and 100?
No, because we're starting. See, but what we want. It's worth thinking about this hard. This is if we start at 1. This is how the human would do it. Now, if this, see here, if we start at 0, if this were 99, we would never hit 99. We would hit 98. Or we stop at, we don't let the loop doesn't run when I is 100. And if this were set to 99, the loop would not run when I were 99. It would only run when I at 98. So it'll go 0 to 98. 0 to 98 is, let's see, 0 to 98 is the same thing as 1 to 98 plus 1 more, which is 99, right? Now this is a problem. This is also representative of a general problem in computing called the one-off error. It's very common to be off by 1. It's 1 too much, or it's 1 too little. You don't know. So you've got to do extra reasoning all the time to check that you're not off by 1. It's like, like your birthday, like how old are you, right? You know, how old are you? Well, you know, you got to know, you know, because I'm 2 ages each year. You know, which age am I this year? Well, it depends on, am I before or after my birthday right now?
Right.
There's a one-off problem when you're figuring out your age, and it gets worse when you get older. So the human, I mean, if you want to write your loop like that, it's fine. Okay, there's no points taken off in the class, but I'll tell you this: that when you read code, that this is what you're going to read. That's what people use. That's how they express it. And it has to do with when you dig down deep and see how the machine is constructed, you know, the counting starts at 0. You know, memory, computer memory is a sequence of bytes. And the bytes are addressable. The bytes are numbered. And there's byte 0, byte 1, byte 2, like that. So it starts at 0. And if they didn't start at 0, it would complicate the hardware design. 0 is the natural starting point. You'd have to have more complicated hardware if you wanted to start at 1. So the languages, computer languages, evolved out of, you know, hardware instructions. You know, hardware instructions are then replaced by assembly language. Assembly language is then replaced by C and, you know, Fortran and COBOL. And then this starting the count from 0 was sort of inherited from that long history of building programs from the early times. There we go. Oh, let's see that run, by the way, right? Let's see that run. So I'm going to make sure that that's written out. Well, there it is. There's 100 of those. Okay, now we have a new problem. Now we've got this part figured out. We know how to repeat something, you know, n number of times. But now what we want to do is replace this value in here with an integer. So let's do, what's going to happen is we're going to generate an integer. Let's call it n. Let's call it 9 for now. And then we're going to print it in here. Nope, that's how to do it. So we're going to generate a random integer. Let's pretend that n is, you know, that this expression is some function that we're going to call to generate a random integer. And then we're going to print it out like this. Before we go any farther, let's just check to make sure that that works. Okay. So now we've replaced that hard-coded 9 with, you know, a reference to a variable. Now we got to figure out how to let n be random. And there is a function called rand. And I think did we do this already? We did, didn't we? We talked about rand already. Now rand requires a header up here. And let's just see this break. Rand is not declared. Let's go back. I think I remember it this time. C standard lib. You don't need to remember that for any test. But when you do your work, you're going to need to figure that out. So that is, of course, in the textbook. There we go. Look at these random numbers. But they're too big. The assignment says somewhere in here. No, I guess that's good enough. I'm not limiting it to a range. You can print out any random numbers. Okay, so that's good. But take a look at this. Look at the last number. 1956. Okay? Now run the program again. 1956. That's the same number. All the numbers are identical. Oh, no, that's not identical, is it? Oh, yes, it is. These are identical. So what kind of random numbers are those? They're not. They're called pseudo-random numbers. And we're going to get exactly the same sequence of pseudo or fake random numbers. So I think we talked about this before. We need to seed the random number generator. We only do it once. We can seed the random number generator with something else, like say 3. Now when we run, we'll get a different sequence of random numbers, but it's the same sequence once again. So we need to some way of generate. We need a random seed. We could have the user input a number and then use that as our random seed. But a convenient way to get a random seed is just to call time. And I think we need C time for that. Let me check if that's the case. Wait, I'm going to comment that out. Shouldn't have any unnecessary headers in there. And we don't need that. We don't need C time. All right, that's not necessary. Let's be in C standard live. So now when we call time, we pass in the argument 0. And I don't know what that represents actually, the 0. But I know the result is we got the number of seconds or the number of milliseconds since a standard epoch. And the standard epoch is normally January 1st, 1970. $479, $121, $672. So I'm reading the first 3 digits of the last number. So now we've got something that looks like random numbers. They're still pseudo-random numbers, but they could be more random. It's not good enough. You know, when you do encryption, you got to have a source of pure random numbers, or good. You have to have a good source of random numbers. This procedure I'm showing you here is a bad source of random numbers. A hacker's going to say, oh, you know, all I have to do is try seed values right around, you know, Wednesday, January 25, or whatever today is. And it is 25. And so the hacker has an advantage. They know how we're generating the numbers, so they're just going to try lots of values and hit the sequence of random values that we're picking from. So this is not good enough for encryption, but it's good enough for simulating random events like that you might see in a video game. Okay, that's it. We're done. That's it. And the only thing is, it's hard to see the result here because it doesn't show up on one screen. So if you wanted to look at it, whoops, that was a mistake. If you wanted to look at this, you'd have to copy and paste. But I'm not going to bother doing that. You know, you've already seen how to do that. Do you want to see how to do a while loop here?
Yeah.
Do you want to see how this is done using a while loop? Okay, let's see that. The while loop. Now let's solve the same problem. We're going to repeat something 100 times. And the while loop has the loop condition in here. this is the code that we want to repeat 100 times. And the while loop is simpler than the for loop in the sense that it's got these parentheses with a single expression inside of it, which is the loop condition. As long as this is true, this will be executed. But for that to be true, I must be, first of all, I must be defined. So let's define it. And then I is like our counter. So we're going to define the counter. We declare int I, set it to 0. And then we do the body of the loop. And then at the bottom of the loop, we have to do this manually now, or we have to do it here. We have to increment the counter. If we don't increment the counter, we have what's called an infinite loop, just because the loop condition is always true. The program will crash. It will freeze. In fact, you know, when you have programs, you're running a program on your computer, and it freezes.
Yeah.
It could be because it's in an infinite loop.
Oh, okay.
And the other reason for a freeze is called a deadlock. Like I'm waiting. I need that chair to do my job.
Right.
But you had a chair. But you're waiting for this to do your job. But I got this. So you're waiting on me to let go of that, and I'm waiting on you to let go of that. We'll wait forever. So that's called a deadlock. And that's another reason when your program freezes that it could be a deadlock. So that's it. This is how the loop is expressed using a while statement. Yeah, question?
Is there also a do while?
There's a do while as well. Is there a do while in C++? You know, because I never use it. So, all right. So do while. Let's take a look at that. You do see it occasionally, and it's not in all languages. But while and for are pretty much in every language. So we're going to do the following. You know, whatever it is. Something. And we're going to do it while x is less than 100. Actually, let's do it like this. Maybe I never use this, so there are good reasons for doing it actually. So the do loop would look like this. Initialize I to 0, and then do this, whatever, and then check the loop condition. Now here, watch this. Let me show you the difference between these two. This is the while loop. This is the do loop equivalent, or almost equivalent. This we're not going to think about. And let's take out what's not important here. This is not important. This is something. That's what we need to do. Okay. This is our job. This is our task. Got to do that. Whoops. So that our task. That's the thing we want to repeat. So this will repeat the task 100 times. And this will repeat the task as well 100 times. We better check that. We start with 0. We do the task. Okay, we did it when it's 0. Then we increment I, become 1, and then this, right? And then when I, at some point, when I is, so we start I equals 0, and then when we increment I, that's the number of times we've done it. So the first time we come in here, When I is 0, we do this, and then after incrementing I is 1. So we've done it one time. So every time after we increment I, that's the number of times we've done it. So we want when I is 99 here, then we do the task, and then we increment I, then I becomes 100, we're done. We've done it 100 times. I less than 100, no, X is no longer less than 100. I'm sorry, it's not X, this should be I. Then we're finished. So that does it 100 times. But let's do this. Let's change the initial state of I to 100. Now what happens? Well, up here, we set I to 100. The loop condition is immediately false, so we don't do our task at all. We do 0 executions of the body of the loop. But here, we initialize I to 100, but wait. We're not going to check the loop condition yet. We're going to check the loop condition later. So we're going to end up doing our task once. Then we're going to increment I becomes 101, and the loop condition fails. So the reason for the do loop is there are situations where you want the body of the loop always to run at least once. And so it's sometimes convenient to use a do loop. So all of this about seeding the random number, and I don't use time 0 in here, do I? I think I may modify the instructions. Also, this doesn't seem to be as important. I'll leave that in there, but I think I may add some instructions on using calling time 0. All right.
Well, if we do it in the lab today, you want us to use time?
Yeah, I want you to use time. Seed the random number generator by using the time function. Let's take a look at assignment 1. Is there anything else I need to talk about? If conditions, we need conditionals, right? Conditionals are covered in reading 3. Oh, so I'm skipping this. This is lab 3. And do we have conditionals in lab 3? We didn't use conditionals yet. I don't have any lab exercises that use conditionals. In lab 4, we use conditionals. All right. I say let's do this. Let's start on assignment 1. Now we got to do this early. It looks like, hey, wait a minute, that's February 6th, right? But this is the right time to start this stuff because you want to get this done well in advance of February 6th and move on to the later material. Let's look at assignment 1. These are short questions, short problems. You don't submit anything to the repository. So these questions you'll answer on Blackboard. Okay, and the grader's going to look at your answer on Blackboard. And so far on Blackboard, we're just typing in yes, I did something, or no, I didn't do something. Now we need to submit some answers. All right, let's look at exercise 1 here. Here's the instructions. When the above code runs, or here's the question. When the above code runs, what does it output to the console? So this is a reading problem. You need to read it. You have to read and understand the code. What does it output to the console? Well, I can just read it to you, right? Let me read it to you. But you have to learn how to read this by yourself. So I'm going to read the first line. Int I equals 0. Okay, that's not good enough. I can't just That's not going to do any good. You have to understand what it is. So we're creating a variable I, initializing it to 0. Okay. Now we have a while loop. Oh, okay. I'm going to repeat these statements while the loop condition is true. So you understand that concept, right?
Yeah.
So let's repeat these statements while the loop condition is true. And let's put our answer here. And let's do a little, let's keep some notes. So we have a variable called I, and we've already set it to 0. And in fact, that's the only variable in the problem, so it's easy. So now this is the output. So I is 0. So 0 is less than 7. The loop condition is true. So let's output this. Oh, but there's 2 operations in there. So remember, you're reading this. You have to say, okay, I got to do one operation first, then I'll do the other operation next. The first operation that you do, let me do it like this. The first operation you do is the multiplication. It has higher precedence than the output operator. So you have to do this. So you take what's in I, which is, oh, we made a note of it up here, 0. 2 times 0 is 0, so we're going to output 0. Okay, so we're going to output 0. And then what do? We increment I. We're not outputting I. We're not incrementing I and outputting I. We're just incrementing I. So that means I got to change my note here. Okay, now I is 1. So this is a note that I'm keeping to myself. Yeah.
No.
You're okay with that? Okay. So now at this point I finished this. Now we're at the end of the loop. The loop is something that you have to repeat. But you repeat as long as the loop condition is true. So we got to check the loop condition. I is 1. 1 is less than 7. The loop condition is true. Okay. Then we got to do this. Don't go too fast now. Doing this means doing the sub-expression first, evaluating that, and taking the result, sending it to the output stream. So 2 times I, that's 2 times 1, that's 2. The 2 gets sent to output. Oh, so we got to just write it right there. You know, on your answer, you could put a space in there if you like. But actually, yeah. But you know, this although the code is legal C++ code, it's kind of meant to be pseudocode. And when you answer these questions, you don't have to be syntactically correct. You have to be conceptually correct. All right. So we just outputted the 2. So now we got to do this. We have to increment I. So I turns to 2. And then we got to check the loop condition. Is 2 less than 7? Yes, it is. So 2 times 2 is 4. We're going to output 4. And now we're going to increment I. I is now 3. You know, we could keep doing this, but, I mean, you get the idea, right?
Yeah.
So it's going to be 0, 2, 4, 6, 8, 10, 12, 14. Oh, but where do we stop here? Okay, let's back up. I is going to hit 6, right? But it's not going to hit 7. When it hits 7, we're not going to do the output. So the biggest I is going to get 6. Right?
Yeah.
So the value at that point, it's going to be 2 times 6, which is 12. That's it. You know, in the quiz, I might give you this. I might give you, you know, instead of 7, I'll give you 27. You're not going to want to add I each time. You've got to do a little extra reasoning, like we just did there, to understand what to do. All right, let's do the next one. Exercise 2. rewrite the above code so that it uses a while loop rather than a for loop to accomplish the same output. So it's just a rewriting problem. So what we have here is a for loop. This is the thing that gets repeated. All right, so we're going to repeat this over and over again. So we're going to have while some condition is true, repeat this. That's the form of the while loop. It's actually can do this mechanically. This is the loop condition. Just put the loop condition in there. And the loop condition depends on this initialization here. And that at the bottom of the loop we do this operation. That's it. Any questions on this one?
Same one as the one above, no?
But the same one in the book?
No, I'm saying the same one as exercise 1. That code that you just wrote was the same as exercise.
Oh yeah, is that right?
Well, the code that you wrote in the notepad, and the exercise 2 it's 4 instead of while.
Oh, exercise 4.
No, I'm saying exercise 1 is the same code you just wrote. Wasn't it? Alright.
Exercise 1?
Yeah.
Oh, look at that. Yeah. I was cheating, you know, I just... All right. Let's do exercise 3. And this is kind of shrinking there. This is the body of the for loop. Okay. How many times does the body of the for loop run in the above code? How many times does this body run? That's the body there. How many times does that run? Well, approximately 100, right? So I'm going to get, well, it's either 99 or it's 100 or it's on, those are my first 3 guesses. I mean, it might be something other than that, right?
What is K?
Actually, K is irrelevant. K is not used. Oh, you know what? I think I had K here before. I is less than K. I'm going to change that. Let me change that.
Trying to trick us, huh?
I meant for that to be K. I'm going to put that in there. Well, you can just replace. What's wrong here? Did I not log in? Oh, I got to edit. You know, I mean, mentally, when you see this, you just replace K with 100 because we don't modify K in the loop. If we modified K, then it would be more complicated to figure out.
Yeah.
So
Function that modified K every time I implemented 1.
so just mentally, you know, envision that you don't see a K, you just see 100. All right? Actually, that K, that threw off people, you know, last quarter. So let's be careful here. So this is 100. We start I equal to 0, and the loop condition is that I is less than 100, and then we're going to increment the counter here. So that means I never reaches 100. Well, I mean, when I reaches 100, we don't do the loop. So that means the last value of I for which the loop runs is 99. 99 is the last value for I for which the loop condition is true. So we're going to do this when I is 0, when I is 1, when it's 2, ... when it's 99. But we're not going to do it when it's 100. So 0 to 99. How many things, how many numbers are there? There's 100, because we're starting at 0. So the answer is 100. I know. I remember some people they put K. What am I gonna? Am I gonna take off for that?
Is that legit? That's legit though.
I gave him full points for that. But I in my heart I didn't want to.
Actually,
Right.
Yeah.
technically it should be K minus 1.
No, the K is 100. The loop runs 100 times.
Yeah. 99 plus.
K minus 1 is the last value that I takes on for which the loop runs.
So we get full credit for book K, right? Good.
I couldn't tell that the student was being, making fun of me, being clever, challenging me. You're going to give me credit for that? Let's see. We have a little more time here. Okay, exercise 4. When the above code runs, what does it output to the console? All right, this is that console problem. All right, here's the console output. All right, once again, we only have one variable to keep track of, so it's easier than if we had more than one. We've got I, we initialize I to 11.
So we're starting at 11, not 0.
Yeah.
Okay.
And once again, we just have to check the loop condition. Each time it's true, we run the body of the loop. And, well, let's just go ahead and do it. Let's pretend we're the computer. Let's run the program. Okay, I create I, set it to 11. This is my memory. Okay, I'm simulating a computer. And now let's compare I, which is 11 to 99. That's true. I is less than or equal to 99. And therefore, we're going to do this. We're going to take what's in I, which is 11, add 3, which is now 14, and then assign it back into I. Now I is 14. You don't want to write 14 for the answer here, right? Because we're not outputting 14. See, the output operator is on the outside of the loop. We haven't done that. So make sure you keep that straight.
Okay.
So after this command runs, this is the state of our memory. I is now 14. And then we do this loop condition. And that's true, which means that we do this. We add 3 again.
Oh, okay, so it's when it's output,
Yeah. Well, we're not outputting anything. So what are we doing here? We're adding 3 to I. And we're doing it as long as I is less than or equal to 99. So let's skip some steps here, right? So, I, the last I, let's figure out what's the last I that's admissible, and then the next I that gets rejected. So I is going to look like this. It's going to take on values 11 plus some number n times 3. That's what I looks like. It's some multiple of 3 plus 11. Those are the values I takes on. Huh? Oh, I'm sorry. No, n times 3, because we add 3 n times. So it's n 3s. We're going to add n 3s. That's multiplication. So let's say we've got 99. If I take out 11, I got 88. And 3 doesn't go into 88, right? It goes into what? 81 and 84. Does it go into 88? Huh?
No.
87. It goes into
The
87.
rule is that you add up all number.
Yeah.
If that number is divisible by 3, then the entire number is divisible by 3.
So 87.
87, 8, and 7.
I got it.
15, divisible by
What's
3.
87 divided by 3?
Well, I don't know that. Maybe get a calculator.
What's 87 divided by 3?
It's 29.
29? Okay. All right, so I think, I is going to ultimately hit this number. Right, maybe. What is that number? That's 87 plus 11. That's 98, right?
98.
So I will hit 98. Now when I hits 98, the loop condition is true, which means we're going to add 3 to I. So now I becomes 101. And then we do the loop condition. The loop condition is now false. So we exit the loop and we print I. I is 101. We're going to print 101. So what we're doing here, we're analyzing algorithms. We're looking at an algorithm and we're analyzing it. We're actually not carrying out each individual step. We carry out a few steps to get the feeling for what the algorithm is doing. Well, we're not going to do this 99 times or, 29 times. We don't have time to do that. So we have to use reasoning like we just did to understand the algorithm. All right. I always forget to cover something, and I know I'm forgetting something now, but I think that's probably enough for today. Is there anything, anybody have a question? If you're having trouble with subversion, please come and see me, or any other problems, please ask me directly now.
Blackboard, do we show the work we did or just what the output is?
Just give me the output. I want to see your output. Don't write down your reasoning. Just show, ask what's the output.
All the computer does anyway.
Yeah, when I ask a question, I want to see the answer to that specific question. I don't need to see your reasoning.